So thank you all for coming. My name is Julie Sutton, and I'm a student at the University of Texas at Arlington, and I work with Dr. James Epperson. And today I'm going to share some interesting results that we got from a master's project that I worked on, comparing emerging scholars students to what we call non-emerging scholars program students at our university in a way where we were looking at their feedback on student work. So I'm going to first discuss the framework that kind of supports my research, the research question that I was investigating, a need to develop an instrument in order to study this question, the administration and data analysis of this instrument once it was given, and then some discussion of the implications. So all of us know that calculus is very, very important, and it serves as a gateway course. So our students who strive to earn a degree in a STEM field, if they cannot get through at least an introductory course of calculus, and in many, many cases, a sequence of calculus courses, they're not going to earn that STEM degree. So as a result, as you all know, many universities offer intervention programs to help support these STEM students, and we have one such of these at the University of Texas at Arlington. So in our particular case, we have a National Science Foundation grant from the Department of Undergraduate Education that helps fund our project, and we target first semester calculus students who are in chemistry, engineering, physics, or mathematics majors. And what these students do is they commit to attending what we call ESP workshops. Depending on the semester when they take these courses, they either attend once or twice weekly, but it's always for 2 hours per meeting. And in the particular semester that we're discussing, these students met for 2 hours on Tuesdays and 2 hours on Wednesdays. So they got 4 extra hours a week in their ESP group setting. And our goal, much as you know from being interested in the Emerging Scholars Program, it's like Uri said, we're trying to build these community of mathematics learners. And as I started to read a lot of the stuff Uri did, he said that he really believes that these students have a differentiated ability, a higher ability than the students who did not take the Emerging Scholars Program courses at critiquing and giving feedback to other students for their work. So I started to wonder about this, and this is the research question that I came up with. How do students who actively create worked examples through meaningful problem solving in small groups view and critique proposed solutions to calculus problems compared to students in a traditional calculus setting? So one thing I want to talk to you guys about is this worked examples. So Sweller has done a lot of work in this series, in this particular field, and I'm first going to explain and give a definition from what Weber says. And so Weber says that a worked example would traditionally be one where you have a technique introduced and you have several mathematical problems where they employ that technique. Does this sound familiar to any of you who use a calculus book? And Leithner has done some work actually reviewing those calculus books and seeing how when you work a problem and you employ this method, and then guess what all the problems associated with that particular section of the chapter do? They employ that same technique. And so through the Emerging Scholars Program, our worksheets aren't attached to a particular section of the book. So they're having to figure out what technique they're going to employ. And as they do this, we feel like they create this library of worked examples. So how this works, according to Sweller with some of his cognitive load theory work, is that you actually create kind of like a card catalog. So imagine those old card catalogs where or a Rolodex. You would kind of dig through. And that's what Sweller asserts our students do when they have this large, expansive, worked example base to pull from. And so our Emerging Scholars Program students, as they work through all their worksheets with these really challenging problems, they're building this library of worked examples. So in order to get some insight into this question, I needed to develop an instrument. So at our particular university, all of our calculus exams are given at the same time on the same day to all the students, and they're written by committee. So we decided to review this common exam before it was given and choose some questions. Now, of the 5 questions that we would call show your work or free response, one of them was totally procedural in nature, and another one was just kind of a word problem that didn't really help us, wouldn't have given us much insight. So we chose 3 of the questions that were left, and in the grading of this exam, what happens is that one instructor grades the same problem on every single exam, 800 times. So we asked these graders if they would help us. And as they were grading, we asked if they would please flag some solutions that students had submitted for this exam, because we could not have come up with some of this on our own. It was a great way to see what, get a large pool to choose from. We also asked that they choose examples for us to look at that were not part of students who are part of this study. So nobody would get the paper and be like, oh, that's my exam. And so we asked that they choose them in 3 categories, and we asked that they flag a minimum of 3 for each category. So a minimum of 9 from each grader. We were looking for poor, mediocre, and exemplary type solutions. So a poor solution would fail to properly show the supporting steps, as they're working through it. And we're especially interested if that answer was correct. How did they get there? Where was the math magic in that? If they made it what we would consider a major algebraic error, or if there was evidence that there was a major or conceptual error going on. So here's an example of something in poor quality. So the question says, use the limit definition of derivative to find f prime of 2 if, and we're given the function f of x is 2 over x. First line's great. Don't know what's happening here. And voila, we get the correct answer. So this is exactly one of those categories I was discussing. We're not sure what's happening in that second one, but we miraculously get the answer. They probably use the power rule. But we wanted to see what our students would tell us about this. A mediocre solution might have that minor error. They might skip some steps here and there. We really wanted some that were technically correct, but they took that non-optimal path to kind of get there. Or something that might be technically correct, but really highly disorganized, really difficult to follow. Now, this is all going to contrast with what we would consider to be an exemplary solution. So it's what you would imagine. All sufficient, or all steps needed are there. They're justified. They support that stated conclusion. It's highly organized, really easy to follow. It's robust and complete, but they might not be perfect. Maybe they fail to follow through with some equal signs, or they make a little algebraic error here and there. So this is an example of what we consider to be an exemplary solution. And so they're given a piecewise function here and asked to find the value of c that will make the function continuous at the point x equals 1, and to justify using the definition of continuity. So in this statement, this particular student makes a general statement. They algebraically find what they're looking for. They make a statement of definition and then a conclusion statement. And it's really pretty. And if you'll notice, this writing looks eerily similar to the writing on the other one. We transcribed all of the student solutions that we chose to use to protect anonymity of the students. So I'm now going to discuss how we administered this particular instrument. So our students at our particular university take a 4-hour calculus course. They meet 3 hours a week for lecture and have 2 recitation sections. One is actually a recitation section with a TA, and the other one is a lab section where they're working on something kind of in groups. So on a particular lab section, after the exam was given, but before the exam had been returned, we gave this assessment to a group of students which were taking the same lecture course, but some of them were in the Emerging Scholars Program and some were not. If you notice, the questions were different colors. That's because we made packets where they were 3 different colors. Each packet contained only 1 question and had 3 proposed solutions for that question, just so that it would be easier to follow. They weren't jumping around. So these were the instructions that we posed to our students. Please consider the following questions and the proposed student solutions. Make corrections to each proposed solution. We also decided to add something at the bottom of each sheet. So remember, they had the question and then the work. Well, we said, after making the appropriate, that's really small, after making the appropriate corrections to the above solution, I consider this to be. So we wanted to know how they thought. Was it not effective, fully effective, or partially effective? And then once they'd finished that whole, let's say, yellow packet, we asked them to go back and rate which solution in that packet was the best and which packet was the worst. Now, we also made sure that the pink packet had 2 exemplary solutions and one that was kind of mediocre, and then the yellow packet had 2 that were mediocre and 1 that was poor. And so there was not always an exemplary or correct solution provided for the students so that they wouldn't be able to kind of compare them. So when we administered this instrument, we told the students that we expected them to work for a minimum of 30 minutes. Now, it's important to note that ESP and non-ESP students were in the room at the same time in their lab section, because that's how they generally met for lab. And they were sitting at tables kind of all together in what they would have been their group for that week for their lab section, but this was an individual assignment. And we also gave red pens to them, A, for clarity of marking, and B, to protect their anonymity. So a total of 84 students took this assessment. Now, we did some quantitative analysis, but this is really just a qualitative talk on what we found. But I did want to share with you that, remember we had chemistry, engineering, physics, and mathematics majors that were really our focus in first-year college students for calculus for our ESP section? Well, there were 14 students in the ESP group that fit that. And in order to make our groups comparable, we had 34 within our non-ESP group. And just some general insight that I noticed as I was kind of going through them was that we had a lot more comments that kind of were meaty, gave me some information written by our ESP students. And it was really surprising. They appeared to look for the rationale on this work for a student they don't know, they're never going to meet. They were really trying to give them kind of feedback. So I'm going to show you some examples right now. So this is a non-ESP student, and this is markings on question 2, proposed solution 1. So this is that one where it was kind of a mystery what happened in that middle step. So this student, these were the only marks on the paper. They circled F of 2, they circled that. I don't know what they're trying to tell me. That's correct. I don't understand, but this is all I was given. This is all they did. This is another non-emerging scholars program student. So this is kind of the end of the proof. They boxed in this. I'm not sure what's written there. I can only assume that this X means that they don't agree with that statement of that the conclusion is -1/2. And they write, because answer equals 0 based on students solving. I don't understand what they're trying to tell me. This provided very little insight to what they were trying to tell me. Now, this in comparison is an emerging scholars program student, and this is fully symbolic in nature. So they didn't write me any words, but they clearly told me, right here is where the problem starts. This is how you fix it. And they confirmed that the answer is correct, but they clearly are kind of indicating this is where we went wrong. So this definitely gave me a lot more insight that the student was able to look at this solution and kind of indicate what's happening. So this is another one that's really interesting. This is Emerging Scholars Program student again. And they write, common denominator would have been easier. And then they provide the solution. But here's where it gets really interesting. Remember how I said they were giving me more insight and trying to give feedback to these students? I think too much work was put into this when there was an easier and faster way that gave you the same answer, and there was less room for mistakes the easy way. So this student, it would appear, was able to kind of determine what pathways possibly you could have gone down for this problem and say, oh, well, this one's correct, and I'm less likely to make a mistake if I do it this way. And they're trying to help this student out and kind of give them that feedback. I found this to be really interesting, and this was pretty typical of things that I would get. Not all of them, a lot of them were symbolic, but I was getting this kind of feedback from our Emerging Scholars Program students, and I was not getting them from our non-Emerging Scholars Program students. So what are the implications of this? Well, these students appear within our Emerging Scholars Program group that it appears that they are building this different kind of classification system than their peers who aren't doing this work. And what do we hear about students who are majoring in chemistry, engineering, physics, and mathematics? What do we hear about their communication skills? They need better communication skills when they get on the job market. We want them to work on their communication skills. These students are communicating at a definitely, for me, more clear level. I could understand better what they were trying to say. And they're also getting really good at this constructive peer review process because they're having to defend their work to someone else and listen when someone's defending their work to them. And through the group work that we do, they're learning to be team players and work out some of those group dynamics. So here are some of the references that we used. And I want to thank you very much for your time, and this is my contact information. Thank you.
You don't have to ask for questions. Here.
So I actually have two questions. So first of all, do you offer emerging scholars for pre-calculus? Like, is it possible they would have taken it before?
We do offer emerging scholars for pre-calculus.
Okay.
This particular semester, I don't think we had anybody who had done both, but we offer it for our pre-calculus too. It's kind of a loop. So they could do pre-calculus 2 and then calculus 1, and then they can do calculus 1 and calculus 2. So it's kind of a spring-fall loop.
The second question is, can you talk a little bit about the quantitative data analysis that you did as well?
I can't accurately talk about it simply because I don't have it right here in front of me, and I would hate to mislead you on that.
I'm just actually wondering what type of analysis did you do? Like just looking
so
at
we were
correct
able to do a
solutions?
chi-square analysis for small numbers on it and determine if there was any differences between how they actually rated and ranked the questions. I mean, when I'm looking at quality of writing and insight, that's really so much qualitative, and that's where I found it interesting. I just, off the top of my head, there were questions where they did have some significant differences, but without looking at it, I would hate to steer you wrong. I'm so sorry. Yeah, no, I did a chi-square analysis for small numbers because of that N12 or that N14.
How do students select into American Scholar Program sections or not? And the question is because could there be a difference between them before they join the section that is not due to what they're doing in the different sections, if they're not randomly assigned to ESP sections?
Well, because we require them to attend extra lectures, we can't really randomly assign them to it, right? We can't say, oh, by the way, you get to attend these 4, because we need them to attend in order to get the full effect of it. So I recruit, we have a couple other people that go and recruit to get them to join it. And so as far as their baseline writing, I actually don't have any information on that. Do you want to say anything to this? Me.
I just want to add, though, that
Sorry.
we do have all background variables on all of the students, and so meaning that we know what their prior math taking experience, what they have taken before in mathematics in high school. We have their SAT scores and things like that to then make some comparisons. And I believe in some of the statistical analysis that Julie did, we looked at those who had had exposure to, say, AP calculus versus those who had not had exposure to AP calculus, and tried to disaggregate that way. But of course, since it was a very small number of students, so we were trying to really look at comparison groups that were the same. Now, in terms of actually recruiting into ESP, that is not as structured as it may be at other places, because we just invite anyone in who is a U.S. citizen or permanent resident who is majoring in chemistry, math, engineering, and they have to be a freshman. And so anyone who wants to elect to be in it can be in it. So there might be a motivation question there, but I think it's probably minimized, though, when we can take the data and look at other patterns. However, what we were looking at here was the ability of ESP students to critique solutions of calculus problems. So because Treisman has claimed in several places, in several talks, I've worked with Treisman a long time, that where he said that ESP students have the ability to critique other students' work sort of at a higher level. So we were trying to investigate, well, can we somehow, with a research study, say something about whether or not they actually are able to critique and produce student solutions that are superior in some way or better in some way than those who don't take ESP. Yeah. So.
I think Brian had a question.
I didn't really understand the connection between your lovely qualitative analysis and the worked examples Rolodex. Did you see examples of behaviors that seem to support that that's what's going on? And where were these students, do you think, would they be acquiring them in section, in lecture, extra ones in lab, in lecture, extra ones in ESP, things like that?
Okay, I want to make sure I understand your question. So you want to, okay, so the first question is kind of, where did I see examples where they might have done this? And your next question was, where would they have acquired them? Correct? Okay, so I'm actually going to start with the second question, if that's okay. So in ESP, these particular students spent 4 hours a week working on problems that, to follow the ESP model, Treisman's model, were really hard. And they would work through them, and they would come to a consensus. They would get feedback from TAs, they would, like, when they would write something up, we would kind of give feedback of, oh, well, think about this, or why did you do this? And so through that, they have exposure to what I would consider to be more worked examples because they're creating these worked examples. So they're exposed to the same thing that their co-parts are as far as lab, what they do in lab, and homework. All that's the same. What's really different is that they're spending this 4 hours a week working on these really challenging problems, working through them, and we can consider those to be worked examples in the sense that they've created the genesis of the created work. And so
So we're completely out of time now.
Okay.
Thank you, Julie. Let's give
Sorry.
Julie and James another round of applause.